Welcome back. Problem 11-33. So statement is the simply supported tapered rectangular beam with constant width B supports the concentrated forces P. Determine the absolute maximum normal stress developed in the beam and specify its location. So you can see this is a simply supported rectangular tapered beam with concentrated forces P at different location. So you have to find the maximum normal stress in that beam and you have to find the location where this maximum stress occur. So let's start with the solution. So first step is that you have to find this reaction forces. Let this reaction force at point A is RA, and this is your point B, this is your point C, and this is your point D. And if you remove this support at point D, so you will be having a reaction force at point D. Okay, this is RD. Okay, now by using symmetrical, about as the beam is symmetrical in the about mid axis, so this RA is equal to RD is equal to P. But I will find out this by using equilibrium condition, that first equilibrium condition is sum of all moment about point D is equal to 0 and taking the counterclockwise moment as positive. So about point D, first moment is due to this force P and perpendicular distance is L by 3, and this is producing counterclockwise moment, so it will be positive. So I will write P into L by 3. The second moment is due to this force P and perpendicular distance is this one, which is L by 3 plus L by 3 will give you 2L by 3, and this is also producing counterclockwise movement, so it will be positive. So I will write plus P into 2L by 3. The third moment is produced due to this RA force into perpendicular distance is L, and this is producing clockwise, so it will be negative. So I will write minus RA into L. So this will PL over 3 and this will be 2PL over 3 minus RA into L is equal to 0. If you take the LCM, it will be 3. Here you will have PL plus 2PL minus RA into L is equal to 0. So we will have 3PL over 3 minus RA into L is equal to 0. So PL minus RA into L is equal to 0. So RA into L is equal to PL, and you will get RA is equal to P. Now you have this RA is equal to P. You can find RB by using this equilibrium condition and taking the upward force as positive. So you can see RA minus this P minus this P. So minus P plus RD is equal to 0. So RA is again P. So P minus P, these two will cancel, plus RD is equal to 0. So from here you will have RD is equal to P as well. So we have calculated these reaction forces. Now what we will do is that we will find the, as we have been given to find out the maximum not bending stress. So maximum bending stress is maximum bending moment into C divided by I. So what we will do is that we will find out the equation of bending moment for different regions. So for region AB, if I cut the beam over here, I will write region AB. So if I cut the beam and draw the free body diagram, so it will be like this. Here you have RA, which is equal to P, and let this distance where we cut the beam is X. So definitely there will be a reaction shear force and there will be a movement. Now we will find this by using equilibrium condition. Let this point is O. That sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about point O, one moment is this P into X. that is clockwise, so it will be negative. The other moment is this counterclockwise, which will be positive. Their sum must be equal to 0. So m minus p into x is equal to 0. So you can see this moment is equal to p into x. And this is for region, I will write for region AB. Now you can see this moment is variable because x, if x increases, moment will increase. Now for region BC, I will show you region BC. So this is the region BC. You can see this region. So if I cut the beam at any point between the region BC and draw the free body diagram, so it will be like this one. So here you have RA, which is equal to P, and here at a distance of L by 3 you have P. Clear. The total length of the beam from here to here where you have cut it is X, and when you cut it you will be having a shear force V and you will having a moment M. Okay, so you can see that total distance is X and this is L minus 3, so this distance will be equal to X minus L by 3, and let this point is 1. So we'll find the equilibrium condition. We will find this moment M by using equilibrium condition, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment positive. So first moment is this P into perpendicular distance is X, and this is producing clockwise, so it will be negative. So I will write it minus P into X. The second moment is due to this P in perpendicular distance is this X minus L by 3, and this is producing counterclockwise, so it will be positive, plus this moment. Their sum must be equal to 0. So I will write plus P into X minus L by 3 plus this external moment M is equal to 0. So minus Px plus Px minus PL by 3 plus moment is equal to 0. So from here this will cut with this, so you will get this moment is equal to PL over 3, and this PL over 3 is for region BC. Okay, you can see that for region AB this moment is variable because X changes, moment will change, but this moment for region BC is constant because everything is constant, so this will be a constant value. Now you have moment, you do not know the I, moment of inertia for the beam, so I will write section properties over here, section properties, which is I, and we know that I is equal to 1 over 12 BH cube. Now if you cut the beam at the mid, because you can see that H is changing at every length, so if you cut the beam at the half and draw the free body diagram, or just like if I draw it over here, that this was the beam, so this distance is given as H naught, and this total distance is given as, if I draw a dotted line, so this is also H naught, and this will be also, this is also H naught, that is given. I will show you over here. You can see this total is 2H at this distance, and here this is H naught. Clear? So, and this length is L by 2. So if you want to take any distance X where you want to find H, so at this distance H you will be having height is equal to H. So we are interested to find out the equation for this H. So for what you can see that we have two right angle triangles. So one is this one, focus on it, and the second one is this, and these two triangles are similar. So what is H? I will write it. Okay, so you can see this distance, this will be equal to h naught, h minus h naught. This distance will be equal to h minus h naught. This distance, this again I will show you this distance, this is equal to h minus h naught. Clear? And now from similar triangles, we will take the ratio of their sides. So if you take h minus h naught, h minus h naught divide by this length x will be same with, that will be equal to h naught, which is the height of this larger triangle, divided by its L by 2. It will, the ratio of their length will be same. Okay, so when you solve this and you are interested to find out h, so this h will be equal to h naught over L into 2x plus L. So from this equation you will get this h. Now you can find the height of the beam at any distance of L. You can just put the value of L, you will get the h height at that instant. Okay, now we know that this I is equal to 1 over 12 breadth into h cube. So if you take the cross section of this, so this will be the neutral axis, this is its b, and this is its height h at any instant h. So again you can just put the value 1 over 12, b is almost there. Clear? And h is this one, so h naught over L into 2x plus L whole cube. This is your I. And if you further simplify it, you will get I is equal to B h naught cube over 12 L cube, and you will left with 2x plus L whole cube. So this is your value of I. Clear? Now again you can see that maximum bending stress is equal to maximum moment into C divided by I, or you can also write it M divided by I divided by C, where I divided by C is represented as S, and that is section modulus. So for section modulus we need I and C, so C will be equal to H by 2, and H is this one, this is H. So you just put h naught over 2L into 2x plus L. This is C. Now we can find S. S is equal to I divided by C. So I is equal to B h naught cube over 12 L cube into 2x plus L whole cube divided by C, which is h naught over 2L into 2x plus L. So when you simplify it, you will get S will be equal to B h naught square or 12L cube into 2x plus L whole cube. Okay. Now we'll move toward bending stress. So I will write bending stress. Again, bending stress is related to a bending moment. So you can see for region AB, for region BC, this bending moment is constant. So the beam size at this stage is also larger. You can see here at this region BC, the bending moment from the equation is constant. This is for BC. BC is constant, and here the height or the size of this beam is larger than that of region AB. So we will consider that maximum movement will occur in this region AB. and not in BC, because this BC is constant. So what we will do is that we will consider for region AB. So region AB. So region, we get maximum bending moment is equal to maximum bending stress is equal to maximum bending moment divided by section modulus. For region AB, maximum bending moment is px. So you can just put the value p into x divided by section modulus is bh naught square over 12 L cube into 2x plus L whole cube, whole square. This is square because, oh sorry, this is square because you can see that this will cut with one of above 2x plus L. So this is square. Let me correct it. Okay, this is square. Now you have this maximum bending stress is equal to 6pl square over bh naught square into x over 2x plus L whole square. Let this is your equation number 1. If you have the value of x, you can put it and you can get the maximum bending stress. But we are interested to find the location where this bending stress is maximum, for which we get sigma max. So what we will do is that in order to get this x, so we will get d sigma max over dx equal to 0. We will take the derivative of this and will equate it equal to 0. So we will get this x. So let's do it. So by taking the d sigma max over dx, we will take the derivative d over dx of 6pl square over bh naught square into x over 2x plus L whole square. Okay. So you will get 6pl square over bh naught is common. So it will be d over dx into x over 2x plus L whole square. Not here, but this is whole square. Okay. So 6pl square over bh naught is a constant. So by using division rule, you will take the derivative. So 2x plus L whole square will, you will take the square of this, so it will be 4. Now derivative of first, which is derivative of x, and the derivative of x is 1 into 2x plus L whole square minus derivative of 2x plus L whole square. So it will be equal to 2 into 2x plus L into x, and we have plus 2 into derivative of the second term x. Okay. Now when you simplify it, it is d max over dx. When you simplify it and you will equate it equal to 0. So if you take equate it equal to 0 and you simplify these terminologies, so you will get 6pl square over bh naught square into L minus 2x. You can, I hope you will do it, 2x plus L whole cube. Okay, now you can see the multiplication of this term and this term will give you to 0 either. So it means that either this term is equal to 0 or this term is equal to 0. But 6pl square over bh cube, bh naught square, which is constant, is not equal to 0. So therefore L minus 2x divided by 2x plus L whole cube is equal to 0. So it means L minus 2x is equal to 0 and L is equal to 2x and x is equal to L by 2. So this shows that at x is equal to L by 2 you have maximum bending moment. But you can see x is equal to L by 2, that is greater than L by 3, and we have seen that x is equal to greater than L by 3 where the moment is constant. So what we will assume that the absolute maximum bending moment, I will write it so that you can understand. Since x is equal to L by 2 is greater than L by 3, the solution is not valid. Why? Solution is not valid because at x is greater than L by 3 you will have a constant moment in region BC. Therefore maximum bending stress occurs at x is equal to L by 3 or x is equal to 2L by 3. So let me show you. So at x is equal to L by 3 you will having a maximum bending moment or at this position, because from this this is also x by 3, but if you are taking from this side, so this distance will be equal to 2x this distance will be equal to 2L by 3. So now put x is equal to L by 3 or 2L by 3 in equation 1. In equation 1, this is equation number 1. So you have to replace x with x by L. So when you put it, you will get absolute maximum bending moment comes out to be 18 PL over 25 BH naught square. So just put this x is equal to L by 3 in this equation 1. So you will get this maximum bending moment. So in this way you have find out the maximum absolute bending moment and its location. These are the two answers. I hope you have enjoyed this video and you have learned from it. Again, I will request those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about latest video. If you have any question, you can ask me in comment section. Thank you for watching.